Going on to section 3 of chapter 4. Here we're going to solve by yet another method, linear equations. It's designated as addition, but the thought behind it is elimination. In fact, some books refer to it as by elimination, but addition is involved in it, as you'll see here shortly. So in example 1, and by the way, we are on page 265 already. Wow. We look at our system of equations. They're both in standard form, as we have over there. But now as we look at them, how about if we put a line underneath them and just add them up? We would get here, this is 2x. Now notice what happens. The y's cancel out. And we're end up on this column as a 12. So what we have done is we have eliminated one of the letters through addition. Solve for x and we get x equals 6. So that's one of our ordered pair members. And then we just put the 6 in one of the equations. I'll put it right here. Transpose it, and we're going to get y equals 1. And we have an ordered pair that's unique, a set of equations that are independent, but yet there's a consistent system because there is one answer. Now, if they were all as easy as the first one, what would the challenge be? So as we look at this second example, we see they're set up in standard form, but nothing's going to cancel. But we know back from chapter 2 that we can modify an equation to make it an equivalent equation by doing the same thing to every term. So for instance, if we wanted the 3y to cancel out with something from here, if this were a negative 3y, that would cause this term to cancel out. So I'm going to multiply this whole first equation by a negative 3. Now, watch what that does. This makes this a negative 6x. This makes this a negative 3y. And this makes this a negative 6. Now, the key is to multiply every term. And this is a negative times a negative. This is going to be a positive here, right? Good thing to check your work. Okay. So, again, we multiplied every term by our negative 3. That gave us a positive 6x, a negative 3y, and a negative 6. Okay, we have transformed that equation. It's not the same equation anymore, but it's equivalent. That's what we're looking for. And then we just copy the other one as it was. So negative, we could put a 1x there, plus now 3y, that's what we were looking for, equals a minus 4. So the second equation doesn't change at all. So now when I put the line underneath, these will cancel out. I have eliminated the y's. And I'm going to end up with a 5x equals a negative 10. Now sometimes doing this you end up with a fraction, and you just have to work with it, but So far this is pretty straightforward. So we divide both sides by 5, x equals -2. So we have our first member. Now we can use either equation, and let's use this one. So we have a negative x, which is a -2, plus 3y equals a -4. So this becomes a positive 2 plus 3y equals a -4. Now we're going to transpose our -2 to the other side. I'm sorry, a positive 2 becomes a -2 on the other side. So this becomes a -6, and we have 3y equals -6. Divide both sides by 3, y equals -2. Now it really pays to check your work. As you see, I could have made an error there had I not checked my work. So let's put that in there. Now as we do example 3, again, we can put a line underneath here. Nothing cancels out, so we have to modify to make something an equivalent equation. And if I multiply this first equation by a what, these will cancel out. Think about it for a moment, because that's what you're going to have to do. And it would be a -4. So this then becomes a -8x, be careful to watch the signs, plus 4y equals a -28. Okay, it's not the same equation, but it's equivalent. And then I just copy this one down. Uh-oh. I'm seeing something interesting happening here. Notice when I put my line, I wanted these to cancel out, and they do. I get a 0 here. But so do these cancel out. I get a 0 there, and I end up with a 27, a -27. And you might say, wait a minute, that's not true. Well, what did we say when we did substitution and we ended up with a not true statement? Well, these lines, there is no solution. These are parallel lines. So they are what we call an inconsistent system, since there are no answers, and the equations are independent. But if you were to graph them, it would look like this. And, you know, the solution is no solution. And that's what it would look like. As we look at example 4, we're going to see something similar. Again, let's work on getting rid of the x's this time. So we're going to multiply this equation by every term by a 3. And it then becomes 9x minus 6y equals 6. And you'll notice something here, -9x plus 6y equals a -6. So when we add these up, this is 0, this is 0, and this is 0. Well, in fact, we have the case in which these are actually the same equation, just disguised in the algebra. So we have here a true statement where they're being the same line, they are consistent because there's an infinite number of solutions. And since the equations are the same, they are dependent equations. And we write the answer in set builder notation. We take any one. we'll say x comma y is such that 3x minus 2y equals 2. Now, could we have chosen the other one? Yes. And when you do these in Math Lab, you'll see there's usually multiple choice. One solution, no solutions, and then they'll give you this one. Infinite number of solutions. Well, we have a quiet moment out here too. Let me jump in with example 5. Now, as we look at the original example 5, there's no one thing that we can do to modify these equations to make them an equivalent equation that will cause something to cancel out. So what we have to do is modify both of them. Now, an interesting note, in the book, they modified this one. So I thought as something different, I'd modify this one. So I'm going to get the x's to cancel out. And again, this is the creative part of doing this. So I'm going to multiply every term here by a negative 5, so that the x and this x, after I multiply it by a 3, the x's will cancel out. Again, in the textbook, they did it to the y's. The y's cancel out. And you could do that too by multiplying this by, let's say, a 9, and this by a 4. So it's a similar thing, and that's a choice you have. So I ended up with this. Now the x's cancel out. I add up, I get a negative 47y, and that equals a negative 47. So I just divide both sides by negative 47. I have y equals 1. And that's where I am right here, because I want to solve now. If my y equals 1, I'm putting it in the first equation, and then this becomes then 3x plus 4 equals 13. I'm going to transpose the 4. This then becomes a 9. 3x equals 9, so x equals 3. So again, they're ordered pair, 3, 1. In the textbook, when they solved for x, they got the 3. Then they had to solve for the y, and they would get a 1. Now, if all of the examples were as easy as the ones we've been doing, again, that would be, not too bad, but they do get a little more challenging. So in example 6, we start off with a system of linear equations that are in fractional form. So the rule is, as we said in chapter 2, get rid of the fractions by multiplying each term by the lowest common denominator. So here we have a 2, so we're going to multiply each term by 2. So we get a negative 2x, and I put that down here. Now note here the 2's cancel out, and we're left with just a negative y. Now here, again, the 2's cancel out, and we're left with a 5. So it's not the same equation, but it's equivalent, and it's without fractions. Now in the second one, our lowest common denominator was a 6, so we're going to multiply everything by 6. So here the 6 cancels out, and we get an x. Here 2 will go into there once, 2 will go into there 3 times, so we get a negative 3y, negative 3y. And then 6 times 0 is 0. So now as I look at that, again, nothing cancels out. But if, as we use that technique of multiplying an equation by something, it makes it a different equation but equivalent, and something will cancel out if we multiply this second equation by a 2. And it's each term. So 2x and a negative 6y. And then 2 times 0 is 0. So this is what we wanted. A term that would cancel out through addition. We are eliminating. So this cancels out. We add up our y's and we get a negative 7y equals 5. And now solving for a positive y, we divide both sides by a negative 7. And we end up with a negative 5/7 for y. Now notice we could have put the negative up there by the 5, but the preferred position is by the division bar. I'm a little bit high on that one. Now this one, and as you see in your textbook, this takes almost a full page. This was our original. We did solve that y was a negative 5/7. I then took this value for y and went up into one of our modified equations. Then I converted this to a positive, and I changed the 5 to 35/7. So when I transpose this, it became a negative 5/7. I ended up with a 37. Again, fractions are a challenge. But now I'm going to divide both sides by a negative 2. And I actually could have put the negative here, but it doesn't make any difference where we put it. And notice this is a fraction that's in a sense divided by sort of a fraction. And then we had said in an earlier chapter we changed division of fractions, again a lot of stuff going on here, to multiplication of fractions, and then we use the reciprocal of a negative 2 becomes in a sense a negative 1/2. I put the negative side over there for safekeeping. And then multiplying, I could cancel here. 2 goes into there once, 2 goes into there 15 times, and there's where I get my answer. So my x-coordinate is a negative 15/7. My y-coordinate is a negative 5/7. We list it as an ordered pair. Now I think I'm thankful that in your math lab you're not going to get many that are this difficult. You may only get one. Most of them will be of the other type where you can either solve by substitution, sometimes they'll ask you for graphing, or addition elimination. Okay, this wraps up topic 4.3.